This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
For this one, Barnabas subunit number, I found the kind of formula from internet and tried to do the calculation. It seems correct. So is it true for the formula?
I haven't looked at seen this before.
Already?
It doesn't seem unreasonable. From what I see, just
So the initial interval is 1, so it start from here. So we go step 1, and we just put in.
See, ones and zeros always simply take you to the lower half of the So it's probably right.
It's okay.
But it's more detailed than I was concerned about. I just wanted you to understand what the principle is.
I know the principle. I just try to find one easy to do the calculation. If your question is, hey, what is the number here? So I get confused. How can I do the manually calculation? No way. Okay. The question is for the.
Let me just do one more before I start. Talk more in the break.
For the JPEG compression, my question here is about the DCT. From the DCT, all we know is the DCT is doing to separate the high frequency signal, right? And
concentrates the low frequency in one area.
So do we get rid of the high frequency from the picture? From the original picture?
Well, it's a choice that we make. It depends on this quantizer.
Okay.
But normally we find that the low frequency coefficients have a very small magnitude. And so if you remove them and it makes very little difference.
So we remove the high frequency or low frequency?
The high.
The high frequency,
because the high frequency is defined in very fine detail.
Because people's eyes not very sensitive to the high frequency.
No, well, it depends on how much high frequency information is there and and our display conditions, as you know, how far you are away, and whether those spatial frequencies are visible to us in the first place.
So actually, because the JPEG is it's a picture, right? So when we're talking about high frequency, low frequency, so actually, what is the frequency here in the picture? Is it color or what?
It's the rate at which the intensity changes across the spatial dimension of the picture. So there's an earlier slide. I don't know, we don't have all the slides here, right?
Probably not all.
So
some slides I understand, so I probably skip.
It's all right.
Not all the slide.
Maybe we talk during the break.
Okay. All right. Okay.
Okay, so let's get underway again. Before I get back to the slide pack, two things. One is a couple of people have emailed me about topics for the project, so that's good. But if you haven't given that some thought, can you get onto it shortly? And we need to email and need to agree by email about the topic. Okay. And the second thing is just a reminder that So we're in week 4 now, so next week, week 5, we'll have a progress test. So the first half hour we'll devote to a short test. I'll give you the one that I used last year, and I'll communicate with you during the week about it. Right? I'm not sure that I'll use the same format, but you should at least see the example from last year. Okay. So I actually added to this slide pack a little bit a couple of days ago, just because the structure made a bit more sense, I felt. So there are a couple of extra topics at the end here before we'll move on to the other slide pack. So we should finish this lot tonight. Maybe we'll get into a little bit of the next one, but we should at least finish this one. So you remember where we were at the end of last week. I kind of squeezed in a bit of a discussion about the H.261 coding structure, and actually if I go to the last few slides, I did this very quickly. I certainly don't want you to kind of memorize this stuff. I just wanted you to understand the logic whereby we define, where we're going to start a picture, and we have a special synchronization code, and then the information that's associated with the picture before we start describing the individual groups of blocks, the fact that we can have some information that might apply to a whole group of blocks, but we might override it for a specific block, and then how this logic makes sense that you could use just a motion vector, or you could have a motion vector plus some coded information describing the difference signal, and you need to define which blocks are coded, this sort of thing. So it's just the logic and the process that I wanted you to understand in going through that. But I went through it very quickly. I just wanted to make sure there were no questions about it before I continue on. So what I'd like to look at now is MPEG-1. Given that, and this is a little bit of a history lesson as well, not because the history is important, but because it helps us understand the technical developments when we see how one was built on the other. So in terms of the timetable of standard coder development, we had H.261, which was finished around 1990, and a different group was getting together around the same time to develop another video coding standard. So the H.261 one came out of the ITU, the International Telecommunications Union, and so it was telecommunications oriented. It was the telcos, the telecommunications companies like Telstra and British Telecom and AT&T and Singapore Telecom and so on, who got together to standardise that. But this second group, MPEG, who's much better known, came out of the ISO, the International Standards Organisation. And the group that formed was called, or is called, it's still going, the Moving Picture Experts Group, and that's where MPEG comes from. And so it was defined, MPEG-1 was the first video coding standard that it defined, and it defined it just after, or in that short period after H.261. And the reason that this different body was looking at standards, because it wasn't concerned solely with telecommunications aspects, but it was interested in stored media and computer applications. So this first standard was optimized for operation around 1.5 megabits per second, because that's a standard, the fixed rate at which you could read a CD-ROM. Of course, you can read that at multiples of that now, but in those early days, that was the standard speed. So the idea was that you would be able to store a movie on disk for the first time, right? That hadn't been done before. And the MPEG specification, or each MPEG specification, actually has many parts to it, but the three core parts are not just video, but also the associated audio, and we will look at audio in the next couple of lectures, and also what's called a systems specification. And so the systems specification is recognising that the video and the audio need to be put together, multiplexed in some way, and there may be some other information that needs to be sent to synchronise those two. So we'll look at a little bit about what is in each of those specifications. So I mentioned that this MPEG specification was intended for stored media in computer applications. So what do you think is the significance of that? If you contrast it with what ITU was doing, trying to come up with a standard for video conferencing, basically, that's what H.261 was doing. What do you think this might mean in terms of the functionality that you might want? Any thoughts? What might you want to do when you're watching a movie that you put into a computer on a disk? Sorry? Well, yeah, there's a question. Yeah, ideally you'd like it on one disk, but just you might want to fast forward or jump to a different chapter or pause, right? These sorts of things, which is not something you want to do in a teleconference. Okay? And so that meant that there were different requirements on the structure of the video coding. So. And that's the primary reason for the introduction of what we might call keyframes, or what was called in MPEG I pictures, I for intra pictures. And that meant that we've talked about interframe coding and motion compensated coding, right? And that's what we do in between these keyframes. But periodically, typically every half second or so, we have this keyframe which is coded independently of other frames. So we code this one a bit like a JPEG image, right? No interframe coding. And then we do differential coding for this sequence of frames in between, and then the next keyframe comes along and we have to encode that one independent of the others. Now that's a little bit wasteful of bits, because if there wasn't much change, we might well be able to predict a lot of that and save a lot of bits. But by having this keyframe periodically present, well, can you see why that's useful in what we just talked about? If we had a long sequence of 10 minutes of video, always each frame coded differentially from the one before, what would that mean?
Quantization error may be...
Pardon?
Quantization error may be get higher and higher.
What gets higher?
When prediction is not correct, that...
Oh, well, one problem could be if there was an error. Is that what you're saying? So an error would propagate forever. But there's another reason in terms of the functionality we just saw, as we're talking about.
It's helpful for if you want to pause
or jump in particular, right? Or fast forward. So if we wanted to jump to a location somewhere near here, if it was all predictively coded, then we couldn't do it, right? We wouldn't be able to decode this frame without decoding all the way back to the start. So, but inclusion of these keyframes means that if I say I want to jump to here, either I just round down and say, okay, I'll start decoding here, or within the machine I can find that frame, decode it, and then encode this one predictively from it. So it means that I can jump to an arbitrary part in the video, which is a useful thing to do. It also means that if I want to, and we'll come back to this in more detail, but it also means that if I wanted to fast forward through the video, I could just play these ones. Right? Just play these keyframes, I can pull them out and play them independent of all the others, so I effectively have a fast version of the video. But we'll come back to that point, that one as I mentioned. So we talked about that.
So keyframe means it divides the video into sections
It does, yes, that's right, effectively. But the keyframe itself is, as I say, just like a JPEG image. It's just coded intra-frame, not inter-frame. So it doesn't do anything with regard to differences between frames. It's coded independently of all the others. Okay, so let's look at a couple of the technical differences between MPEG-1 and H.261. Many things were in common. It uses that same basic motion compensated DCT transform structure that we investigated. It uses the same chroma sampling of 420, which means we subsample the chrominance by a factor of 2. Uses that same zigzag coefficient scanning pattern, but it introduced a few differences. So one of them is bidirectional prediction, which we'll talk about in just a second on the next slide, and the resultant different frame structure. So don't worry too much about that. We'll explain that in just a second. In fact, it introduced half-pixel motion estimation. So remember we talked about sub-pixel motion estimation. So this is an example where it was used, and because it improved the prediction and the quality was a bit higher than H.261 was using, they dropped the loop filter. And just with the experience of coding using H.261 and more tests with human subjects, they just used a more sophisticated quantization method, but that's kind of detail. But let's talk about these features, because these are the ones that really distinguish the MPEG encoding structure. So what do we mean by bidirectional prediction? Well, ordinarily, or the way we've described predictive coding and motion compensated coding so far, we would look at our video frames in their time sequence, and when coding a block of pixels within one particular frame, we would, say this one, we would perform motion compensation by performing motion estimation to try to find a match back here in the previous frame, say the previous frame or a previous frame. And so then that would improve the prediction for that block of pixels, reduce the prediction error, and save us bits. What bidirectional prediction does is give us the option of also predicting from a future frame, which you might think is a bit disturbing. We're looking forward in time, but it will make sense. And so what we can do is, I'll get to that in a second. So what we can do is use the forward motion vector, or use the backward motion vector, or use a combination. Whichever the encoder thinks gives our best prediction, we can use that. And we can look at this bidirectional prediction in a couple of different ways. One is that we can just say, well, it's normal predictive coding. That is, we get motion vectors and that gives us a prediction, and then we encode the motion vectors and we encode the prediction error that is left behind. But commonly the way this bidirectional prediction operates is that it's essentially an interpolating filter. It's kind of filling in the gap in between these frames without sending in very much prediction error in to correct the error. So I'll try to explain that a little bit better with this slide. So let's just think about the one-dimensional case. A perfectly valid way of encoding a one-dimensional signal sampled as we see there would be to filter it and subsample it. Right? We're throwing away some information, right? But that's okay. If we're prepared to suffer some distortion, one thing we can do is filter, subsample. In fact, this is exactly what we do with our chrominance component. We subsample it, we encode it, transmit it, decode it, and then when we ultimately display it or present it back to the end recipient, we upsample it, right? We interpolate it. We obtain all those orange sample points. We guess what those orange sample points were by filling in the gaps. Right? So let's just think about doing exactly the same thing in 2 dimensions with pictures, with video. So that would mean that what if we only encode some pictures but interpolate the missing ones? But the problem is that simple linear interpolating filters aren't going to work. Why aren't they going to work? maybe it's already obvious to you, but let's look at this very simple example. If we're encoding the Star Wars 3 movie and we've got these lightsabers flying about all over the place, this is frame n-2, this is frame n, and we're going to interpolate this one. What happens when we do pixel by pixel averaging? We end up with 4 lightsabers instead of 2, right? Because we're not taking account of the fact that the motion is non-linear, right? It's not even that it's non-linear. It's that the motion is along a trajectory in time. We can't just average the pixel locations. So what the B picture, the bidirectional prediction process is, could also be seen as an encoder-assisted non-linear interpolation filter, right? Because the encoder provides the motion vectors to allow you to interpolate this missing picture properly. Does that make sense? No. Okay. So if we try to interpolate between these two pictures just by doing pixel by pixel averaging, this is what we get. So we need some. And the reason that occurs is that the motion is along a particular trajectory. It's not. We can't just average the pixels. So we can improve our interpolation of this missing picture if we get some information from the encoder that assists us to tell us which part of each of these pictures we need to shift to get the interpolation. And that's exactly what our bidirectional, our two-directional motion vectors are doing. Okay, so that's why I said in the previous slide that, or this earlier slide, that we can either look at this as the best prediction we can make and send the prediction error, just as we have done in the past. It's just that we have this additional motion vector from the future, the future slide, future frame. Or we can just think of it as a means of interpolating to find missing pictures and therefore save bits by not encoding it, or only encoding the assisting information. So, sorry. So, bidirectional prediction involves motion estimation forward and backward in time, but we don't require a time travel. We don't require time travel. All it means is that we just don't process the pictures in their time sequential order. So we've got this series of frames that we want to encode. We can encode and send frame number 1, encode and send frame number 2. Then we encode and send frame number 3. We're buffering it, right? And then we interpolate or do the bidirectional prediction on frame number 4. Yeah? Why do we do that? Well, we need frame 3 and frame 2 to do the predictions for what I'm numbering frame number 4. Yeah. So that's why we don't worry about this one. We encode 2, then we just hold 4. We hold this frame in a buffer. We encode this one. Having encoded this one, and we'll talk in a second about how we encode this one, we can interpolate this missing one. We can send the bidirectional motion vectors to describe this one. I think it'll make...
The third frame is ahead of time 4, right?
That's right, but it just, again, it's just a matter of buffering, and then you sort out the presentation order. But yeah, this is a point which I think you've picked up on, right? We don't. Not only do we not process the pictures in their time sequential order, but we don't send them in the time sequential order either, and we'll see that in just a moment. So, as a result of the use of these bidirectionally predicted pictures and the key frames, this gives us the distinct picture structure which emerged in MPEG. It hadn't been used before. So periodically we have these I pictures, the intra-coded pictures, and they're coded independently of all the others. They're like JPEGs, as I said earlier. In between, we have some number, and it's a parameter that can be described, of what are called P pictures. So they're just ordinary predicted pictures, the ones that, as we have described earlier, when we developed that standard model of a basic video encoder, we added motion compensation to it. The way that the pictures were encoded in H.261 was the way these are encoded. So they're simply forward predicted, such that this picture is predicted from the previous I picture, and this one's predicted from the previous P or I, whichever was closest. This one's predicted from the previous P or I, and then we get back to this one, which is encoded independently. Then in between the P and I pictures, we fill in the pictures with these B ones, with these B pictures, and they are predicted both forward and backward. Okay, and as I say, it depends on the settings in the encoder, but quite often we're virtually only sending motion vectors for these guys, forward and reverse direction motion vectors, and very little prediction error. So these are effectively just being interpolated using the assistance information from the encoder. Right. So the B pictures are predicted from past ILP and future ILP, and the P pictures are predicted only from past ILP, and the I pictures aren't predicted at all. Yeah. Okay. So what do you think would be the transmission order here? Just to check on understanding here. If we, let's say the first frame we encode and send is this I picture. Which would be the next one that we want to encode and send? Which one? P, this one. Yeah, that's right. Why? Because we need to encode it so that we have a version that we can use to encode these ones, and the decoder needs to have this before it can reconstruct these ones. Everyone see that? Yeah? Okay, so indeed, once we've sent this P picture, then we can encode and send this B, we can encode and send this B. So what's going to be the next one? The second P, that's right. This one will be the next. That's right. So the sequence will be as shown. Okay. The decoder will store them in the buffer, that's right. Okay, let me give you a different scenario. Just let's talk this through to make sure we all have an understanding of what the issues are. One thing we could do, that's one possibility. As I said, we can encode and send this one, encode and send that one, then encode and send these ones. We could encode and send this one, encode this one but store it at the encoder, just buffer it. Then we could encode and send that, and then encode and send that, and then send that one. Why would you not do that? Or what would be the advantage of doing it as we've described it there? It's a bit to get your head around, imagining what the encoder is doing, what the decoder is doing. But at the decoder, there's an advantage.
There's no need to process these images at the decoder if we send it in the right order.
No need to process them?
Yeah, because we don't need to reorder these pictures at the decoder. Make it easier at the decoder.
It's easier at the decoder, but I'm not sure that it's for the reason that you're saying. Yeah. At the
So if we send the B and kept P in the buffer of the encoder.
no, if we encode and send the B, but we're keeping the P in the buffer in a buffer in the encoder. So we're going to send them in time sequential order. But if we did that, then Let me remove those numbers because it's confusing. If we did that, then we would be sending this B to the decoder, which can't do anything with it. So it just has to store it in memory. Yeah? Then we're sending this one, which it can't decode, so it stores it in memory. Then we're sending this one, which it can put in memory and decode, and only then can it decode and display this one and this one. So we just save a little bit of memory in the decoder if we send in this order. So the decoder can decode this one. It has to buffer it, but it's immediately available to decode and display this as soon as the data arrives, and decode and display this as soon as the data arrives. It also, I think it would also smooth out the processing demands. I have to think that through, but I think that's the case.
Buffering can be avoided.
Pardon?
If you can send them in a time sequence, buffering can be avoided at decoder.
Yeah, there's be more buffering required of the decoder.
Yeah, which one going to be decoded first before the 2B? Which one?
Oh, well, you would decode this one and display it because it would be the earliest one to display. Yeah, because once it's displayed, you can throw the data away. And you free up the memory to deal with the next one.
So if the second B is predicted by full and fail prediction of second B, but what about the first B? Different.
Oh, that's also predicted. Sorry,
Also
also
predicted from I.
predicted like that from the previous I and the following P. So
But if in this way, then two frame, 2B frame, it could be the same.
it's
Because
possible,
it's
but
the same source to doing the decoding.
they require the same reference frames, but they wouldn't necessarily be the same. You wouldn't expect them to be the same because they have been captured at different time instance. So the motion vectors that are calculated to predict this one you would expect to be different to those used to calculate this one, to predict that one. Okay, so we have a hierarchical structure in the MPEG video sequence as well, kind of similar to what we've seen before in H.261, but we have this additional level, which is this group of pictures. So if this group of pictures between I pictures is called a GOP, a group of pictures. So we've got this whole picture sequence which has some certain parameters associated with it, the resolution, the frame rate, these sorts of things that apply to the whole sequence, say the whole movie. But then each group of pictures is distinguished by having an I picture at the start, and so there's a resynchronization point there, and a time code's included. And then each new picture is has a I think there is some there must be a synchronization word, and also labels to say whether it's an I, P or B picture. Where in H.261 we had the picture split up into group of blocks, remember, the GOBs. Here we have just a more generic or more flexible structure. So we have slices, which is the term that MPEG used for a group of macro blocks. So this slice could be across the whole picture, or it could be just part of it, whatever was your design decision. And then, as before, we split this slice up into macro blocks and into the blocks that go to the DCT. Right. Okay. So another feature of the MPEG-1 specification. So it isn't well understood. You may have some familiarity with MPEG-1, but you probably wouldn't realise that it was actually that the parameters that were allowed would permit you to encode a picture as big as 4095 by 4095 pixels, and to operate at more than 100 megabits per second. Remember I said it was optimised for just 1.5 megabits per second. So I think it's interesting to spend a moment considering what happened here, because and the motivations of a standards body. Because if you get lots of experts together and it's a very expensive process, you meet 3 or 4 times a year and invest a lot of time and effort in this standard, you ordinarily would want it to be used as widely as possible. Okay? And that was the case with MPEG. So that's why they designed this thing to operate with such very high resolution pictures and high encoded bit rate, so you could operate it at very high quality, even though the main application was seen to be on CD-ROMs. However, they recognised that if someone was going to build an MPEG decoding chip, they weren't going to build in that much memory or processing power, particularly back in the early 1990s when memory and processors and CPUs were much more expensive than today. So the solution that was adopted was to recognise that practical implementations wouldn't support the whole range, so they defined what's called a constrained parameter set, which is oriented towards the particular target rate and quality for the stored computer applications. In other words, I can say I can produce a decoding chip that operates at only, we'll look at the parameters in a second, but only say 1.5 megabits per second for a limited resolution range, but it can still be compliant to the standard because it's just compliant to the constrained parameter set. So to look at the numbers, so the constrained parameter set, and of course I don't want you to memorise these numbers, but it said that you could be compliant with MPEG-1 constrained parameter set so long as you could accommodate a horizontal size up to 768 pixels and a vertical size up to 576 pixels. These are standard TV resolution type numbers. Certain number of macro blocks, maximum number of macro blocks per picture, certain maximum number of macro blocks per second, because that determines how fast your processor has to be. Maximum number of B pictures in between the I's and P's of 2, so it couldn't be greater than 2. Operating up to 1856 kilobits per second. So that provided a kind of reference point that you could say, I am compliant with MPEG-1 constrained parameter set, and would mean that I didn't have to produce chips that operated at those very high resolutions, very high rates, at a time when no one had an application for those sorts of that sort of performance. So commonly the implementation was even lower resolution, bit rate of 1.1 megabits per second to fit easily on a disk, and at a lower resolution than that. But by defining this constrained parameter set, it just meant that there was a point at which manufacturers could target when they were building chips. Okay, so we covered MPEG-1 a bit faster than we covered MPEG-2 because I just wanted to, H.261, because I just wanted to look at the main features of it and where they came from. And so let's do the same with MPEG-2. So with MPEG-2, well, MPEG-1 introduced this main innovation was this IPB picture structure. What came with MPEG-2 was interlaced video. We learned what interlaced video was back in the first lecture. So MPEG-2 was optimized for higher rates and higher resolutions and higher quality, and in particular it was TV oriented. So it was developed at the time that digital TV and high definition TV were just emerging, and in fact I won't go into detail about this, but it really represents a major success of the standardization, because it really was just at the instant when there were several proprietary digital TV systems being developed by different companies, and of course those companies wanted to dominate the market. But it was heading towards the old VHS and Betamax situation, which is possibly ancient history for you, where we would have multiple solutions and that would be incompatible. So MPEG-2 arrived just in time and became the globally adopted system for digital TV and DVDs. So the main feature, though, there are other details that we look at in a second, but the main new feature, the main new capability that was required in MPEG-2 that wasn't in MPEG-1 was to accommodate interlaced pictures, because it was for television applications. So the main differences are that it's capable of coding interlaced as well as progressive video. Because it was intended not just for distribution to television sets, but also within the television community or the television industry for exchange of programs and sending high quality video between studios and into editing suites and so on. They wanted to allow for high resolution chrominance. So instead of just 420, and we recognise why we want 420 to deliver to an actual display for someone to look at, they allowed for these higher resolution chrominance samplings because that was good for maintaining the highest quality when you're going into an editing process before you generate your final program. Profiles and levels we'll talk about with another slide. It's actually a generalisation of that constrained parameter set that I just talked about. A bit more efficient quantizers and code words. That's just with increased experience and optimising for the new application. And the idea of scalability was introduced here. And so scalability we talked about with regard to JPEG 2000, if you remember. It's the same concept. So the idea was that if we could structure our coded bitstream in a suitable way, then if we just take part of that bitstream, we might be able to decode and display something of lower quality. And if we take more of the bitstream, then we get the higher quality. So it's making the lower quality version a subset of the higher. But we'll come back to that. Let's focus in particular, though, at first, on this interlaced video structure, because that's the defining feature of MPEG-2. So just a reminder of what that's all about, and we'll contrast the two situations where our TV coder, our MPEG-2 TV coder, has an original source that's film is transferred to video, or a live camera, where the live camera would be interlaced. So TV interlacing, if you remember, was scanning all the odd lines in each frame and then going back and scanning all the even ones. And as a result, each frame is composed of two fields, and they are sampled at a slightly different time. And with Australian TV parameters, that would be a 50th of a second apart. So what does that mean for our video signal? We did talk about this a bit before, but we scan our orange circle, our tomato, whatever it is, at one time, and then by the time field 2 comes along, the tomatoes move a little bit to the right, and so instead of having a smooth representation within a whole frame, we end up with this jagged edge. And I think I showed you an example of a video frame, a real video frame from TV in the first lecture that showed this jagged edge. If we are transferring from film, however, even if we're doing an interlaced scan, we hold our frame of film steady in our telecine, if you remember the telecine device, and that film frame doesn't move in between the fields, right? So we end up with a smoother edge to our object when we combine the two fields together in one frame. Oh, sorry, I have an example here. So this is an interlaced frame. So if we take both fields and put them together into a frame, we end up with these strange effects as a result of the movement between these fields. So if we think about a block of pixels that we want to transform code, what do you think the result of that interlacing would be? We understand transform coding now. We understand the assumptions about the picture in particular that we use when we transform code, and how we can throw certain coefficients away and so on. What do you think this would do to it? Any thoughts? What's the underlying assumption of the structure of the picture if we're going to transform code it and throw away the high frequencies? We're assuming that the intense. Sorry?
Low frequency has the main.
Yeah, the main energy is in the low frequencies. We assume that for most pictures, that most pictures have intensities or colours that change only gradually across the frame, right? So if the luminance or the chrominance signal changes only gradually, then it's composed of only low frequencies. And so when we go to the transform domain, our high frequencies will only have very small magnitudes and we can throw them away. And it's the short version of what transform coding is all about. Yeah? Okay, so what's this? What are the frequency characteristics of this going to be, do you think?
High frequency.
High frequencies, in particular vertical high frequencies. Right? So our model is going to break down. When we compare the video camera source, the interlaced live camera source against a film source, we'll have this difference. The video camera leads to greater changes between the lines in the frame because of the interlacing, and as a result it's going to be harder to code. We'll talk about how we can code it in a second, and it's going to require more bits. So you might think, well, why don't we just do everything at using progressive scanning at the lower frame rate, like film? Why don't we capture everything on film, or why don't we just use progressive coding on film? And the reason is that it doesn't capture motion as well. So film, because it samples at only 24 frames per second, the motion is more less smooth. It's there's the moving objects are seen to jump across the frame, and you'll see this in the cinema. But even though I think I might have mentioned this before, the director or the cinematographer would typically structure the angle of the camera to try to minimise this effect. But if there's a lot of motion across the field in a movie, then you get this visual effect. So, particularly for sports, for instance, it's much better captured on a 50 or 60 field per second interlaced camera. So we have this problem that anything transferred from film doesn't capture motion as well, but it's easier to code because the frame is consistent. It doesn't have this this cone edge type appearance. But interlaced video captures motion more accurately. What do we do about it? So, in the end, you would realise that depending on the content, it might be better to code some video as a frame or as fields, right? And so, for that reason, the solution that was adopted in MPEG-2 was to define a frame picture structure or a field picture structure, and instead of taking our 16 by 16 macro block from a frame, we allow for the possibility of splitting it into two halves and taking it from a field, or taking one half of it from each field and calculating the DCT based on the field. I'll show you this in a second. There's another consequence for the block scanning pattern, but we'll talk about that in just a moment as well. So first, let's think about these field blocks. So the idea would be that where in a normal progressive scanned frame, we would have a 16 by 16 macro block, and we would just perform motion compensation on that macro block, and the prediction error would be sent to the DCT just as 4 blocks of DCT, right? But if we're going to have this problem that there's a poor correlation between the green scan lines and the grey scan lines, right, the two fields, then we allow for the possibility of separating them out and processing them according to their individual fields. Right, so all the odd lines are sent into one array, which is 16 by 8, and the even lines are sent into a second array, which is 16 by 8. And then we perform motion estimation for each of these just within their field. Okay, so, oops, sorry. So what are the consequences of that? Well, one is obviously that we have twice as many motion vectors, right? Because we've got one for each of these field blocks, whereas before we just had one for each full macro block.
So we did interlace this block again, like, or it's like interlaced?
Sorry, well, if the signal is interlaced, then we're saying that we perform the processing, the coding, on an array of data from within the field instead of across the frame. Is that what you're asking?
I mean, you took this 16 block and you interlaced it again, like.
Oh, sorry. Yeah, yes, we encode it like this, send it to the decoder, and then the decoder puts the two fields back together. Yeah. Okay, so just a question on this. If this is a solution for the case where we have interlaced content, why wouldn't we just do that for all video? Right? We don't have to make a decision. We just take every 16 by 16 block and split it into these two field blocks and encode each separately. Why wouldn't we do that for all video? Say a progressive scanned one that comes from film, why wouldn't we encode it like that?
So because we're gonna throw like small, we said before that we're gonna throw high frequency for the whole picture.
Yeah.
But in here we divided the picture into smaller frame, like smaller section.
Yeah.
So
So there is already some correlation between these frames. There is always a prediction that we are doing here.
Yes, there is. Yeah.
I think the picture will become more smoother than like it won't show as much as we do for the whole frame.
I'm not sure if I understand precisely what you're saying, but the issue would be that ignoring what's on the right, let's just get rid of it temporarily. If we encode that 16 by 16 array as one, and it was a progressively scanned, essentially still image, sorry, not progressively scanned because I've got separate fields, but the object had not moved between the two fields, is what I'm trying to say. So it came from a film, original. Then there would be very good correlation between this scan line and this scan line, right? And between this one and this one. And that's what we exploit using the DCT. But if we took that picture and separated out the fields like this, then these two scan lines that constitute this this block were physically separated more from in the original. So there might be better correlation between these two in the case when it was interlaced, but there's probably better still correlation between these two because they're geometrically or physically closer together. Yeah. So we've separated out. We're trying to look for correlation across a vertical set of pixels, which are effectively sampled at a lower density than this original one. Yeah? Anyone not see that? Okay. So, in other words, we're looking for that structure that gives us best correlation between our blocks of pixels and therefore the lowest bit rate. Ultimately, of course, that's what we're after, the lowest bit rate for a given quality. So we would hopefully have some intelligence in our encoder to be able to make that decision. Do we encode this particular 16 by 16 block as a frame block, or do we separate it out into two field blocks? Okay, so I mentioned that there's an alternate block scanning pattern. Do you remember this zigzag scanning thing when we talked about JPEG, actually? And it's exactly the same zigzag scanning pattern that's used in H.261 and MPEG-1. Do you remember the reason why we had that zigzag scanning pattern? Anyone?
Because
Does-
the energy is not the
So we save bits. We're concentrating our energy in the top left-hand corner, and it's more or less symmetrical between horizontal and vertical directions. So by scanning in this way, we'll get to the last non-zero coefficient earliest. That's the on average. So that's the theory behind it. So what do you think would be the case if we are encoding these field blocks, or we have some degree of motion between fields which causes this increased vertical high frequencies? Do you think that, what influence do you think that might have on this, or on the distribution of the coefficients?
So maybe high frequency in the vertical section.
Yeah, exactly. So our assumption here is that we've effectively concentrated the energy up in that top left-hand corner, but and there would be relatively low magnitude coefficients in the high frequency areas by both horizontally and vertically. But as a result of this interlace thing, we're going to get a greater magnitude of high frequency vertical coefficients. Even if we encode them as field blocks in that previous diagram, because of that reduced correlation between these pair of pixels compared with these ones, we are still going to have increased vertical high frequency components. Yeah. And so for that reason, when MPEG-2 was doing when the MPEG group was defining MPEG-2, they allowed for an alternate scanning pattern, which looks kind of crazy, but if you take a moment to see what it's doing, it's just putting more emphasis on these vertical high frequencies, so they're scanned out a little bit earlier than the other ones. Yeah. So again, of course, I don't want you to reproduce that. I just wanted to get across the logic as to why we would want to do this sort of thing, because we can expect increased high vertical frequency components, and so there'll be a little flag in the coded video sequence to say that for this macro block, for this block, you should use this scanning pattern or this one, depending on which one is more efficient. Is that okay? Gone through a couple of challenging concepts there, but hopefully it makes some sense. So, don't want to take the time to talk about this alternative chrominance and luminance sample position. I suppose having it on the slide, I just need to say what I'm talking about. If you remember, back when we were talking about doing 420 subsampling, reducing the resolution for the chrominance signals, we created a pattern of chrominance samples where the chrominance was an average of the surrounding 4 pixels, and therefore it was logically located right in the centre, in between them. So what this dot point is, and sorry, I shouldn't have bothered with it, I don't think, is that with MPEG-2, that physical location of the chrominance samples was not necessarily well suited to this interlacing, as you might expect, because some of those some pixels come from one field, some pixels come from another field, and so they allowed for different definitions. But I don't want to say anything more about that for now. But I did mention that MPEG-2 was intended to support higher chrominance resolutions for the purposes of supporting higher qualities for to deliver high quality video source material into editing suites and so on. But if we do that, that also means that we have new macro block structures, right? Because you remember how the macro block was defined in terms of 8x8 blocks in what we've discussed before. If we're using 420 sampling, the chrominance and the CR and CB chrominance components have 8x8 resolution that maps onto this 16 by 16 luminance resolution, so we end up with this 6 blocks to process. With these other sampling patterns, we end up with different structures, so that also needs to be accommodated. And in the case of 444, there's no chrominance subsampling, so each macro block consists of 12 blocks, each of which goes to the DCT and is quantized and so on. Yeah? Okay. Now, the profiles and levels thing. So, the idea of profiles and levels in MPEG-2 was the same idea as the constrained parameter set. Exactly the same objective. We want our standard to be really widely adopted for all sorts of applications, particularly throughout the television industry. So we want you to use it for HDTV. We want you to use it for inputs into editing studios. We want you to use it for 3D. We want you to use it for distribution to your TV audience. And we want to use it in DVDs, in fact. But we also recognise that no one's going to build chips that include all that functionality. So if you wanted a really simple, low-cost receiver, you're not going to want to build a chip that does HD and does 3D stereo imaging and stuff like that. So their solution was a generalisation of this constrained parameter set, and they defined 2 axes. One which is resolution, picture resolution, and one is the functionality. And so whereas in MPEG-1 we just had one constrained parameter set with limited functionality, limited resolution, in MPEG-2 there were specific combinations of the 2 that were defined. And these are those 2 axes ended up being called profiles for functionality and levels for resolution. So the idea was that maybe some people would want to build really simple, cheap decoders. Simple meaning no B frames, no B pictures, and perhaps very low resolution, just half standard TV resolution. Then there was the main profile that had all the capabilities of the IB and P structure. There was the 422, there was stereo vision, these sorts of different functionalities. I won't worry about the scalable ones yet because we haven't talked about it. And for each of those different profiles, different sets of functionality, maybe we want to be able to operate at different resolutions. So maybe I want a main profile format that includes the IBP structure, and I want to operate it at standard definition TV resolution, but also high definition TV resolution. And so hence the two dimensions, and these which can be sort of represented slightly differently here, where we have the profile of different functions and the level of different resolutions. And then for, say, conventional TV broadcasting using HD, I want this, high, main profile, high level. And for TV production, maybe I want 422 profile and main level, or some other combination. Does that make sense? Yeah? Now, standards bodies can't necessarily predict exactly what the market will adopt, particularly as time goes on. So there was an assumption that this low complexity profile, the simple profile, would be a useful thing to include, but in fact no one used it. It was lower resolution than was required. It was not good enough for TV quality, not good enough for DVD quality, or DVDs had come along and they had enough storage capacity, and the interface rate was high enough that that you didn't need to sacrifice picture quality that much. So this was just never used, but that's okay. The other ones were certainly used, and the MPEG-2 standard has been highly successful. Okay. So those three coders really provide the basis for subsequent coders. We're going to talk a little bit about some of these more recent ones, but the core coding tools were essentially developed with those three. But what I wanted to talk about next, and I'll do so after we have a little bit of a break, are these issues of rate control and whether the bit rate that we're generating from our encoder is constant or is it variable, and what we do about that. And also, we keep talking about quality, so I want to just talk a little bit about how we actually measure it. So we'll get on with those after we have a bit of a break. Okay. And then, unless you tell me you'd like to do something else, I'll assume you want to just push on and then just finish somewhat before 8 rather than have a second break. I promise to finish before 8 this time. So, have a stretch, wake up. I'll try to do the same. Mm-hmm. Oh, okay, yeah. So, sorry, maybe I wasn't clear. The report or the project is supposed to be essentially independent of the lectures. I don't want you writing a report back to me about what I covered in the lectures. I want you to research beyond the lectures. So to discover new things and discover what's interesting to you. So you shouldn't expect what you're doing in the project to be included in the lectures. I might do some sort of introductory stuff. I think we were talking about reasoning. Is that right? Yeah. So I'll describe those basic techniques. But, I would expect, if that's what you'd like to work on, I'd expect you to go into more detail and look at other techniques. I don't know, maybe consider holograms or something, whatever you're interested in. The objective is not for you to kind of write an assignment about what I said, what I present to you. So what we are. Okay, thanks.
Something people can see, or it's just some kind of number, or what is that?
No, it's
Just being confused.
Yep. Let me kill that. I think it was in the previous slide packs.
So in week 1 or week 2?
2, I think.
That's okay. Look at this.
Maybe not. Here. So remember this one? When we talked about an array of numbers in a frequency domain.
Oh, yeah. Yeah.
Right. So this is defining. This array is defining how rapidly the intensity changes in this horizontal direction.
Yeah.
So that a very high horizontal frequency looks like this. So it's hard to see in that diagram.
Oh, so it's cream.
So, right, with black and white lines very close
black
together.
and white. Oh, yeah.
Right, and back here they would be stretched wider apart.
Oh, yeah.
Right?
Okay.
And over here where there's zero frequency. Zero frequency means no change, so that's just a uniform grey. Okay.
Yeah.
So, and then because we're talking about a two-dimensional array, we need to consider frequencies in the vertical direction as well.
Yeah.
So this is a high vertical frequency,
Yeah.
and that's a high frequency in both directions. Right?
Are they? Is that thing is just like combined from each pixel or what?
What do you mean combined from each
I
pixel?
mean the frequency. See, we can see each line here.
Yeah, that's right.
It's actually so each pixel is the.
Well, the highest frequency you could represent would be alternating black-white pixels. But that's not as high as that. I mean, that's not that high because we can still discern them.
Oh yeah.
The other diagram that might be
correct.
the other diagram that might be interesting would be
Oh, I remember a picture.
remember the one.
Is that thing we're talking about?
Yes, yeah, that's right. Okay, so we have increasing horizontal frequency going this way because the lines get closer together. It's like think of a time sample, which you're more used to thinking of frequency, in which the peaks are closer together in time. That represents a higher frequency. Now these peaks are closer together in space. Represents a higher
So
spatial
that means
frequency.
if we go very high frequency, so if we go that way all the way down, we still. So for people eyes, we can't see. It's not much different, right?
No,
so this one, if we can get rid of the high frequency data or signal,
Exactly.
so it's not going to affect anything for people
That's
eyes.
right. Yeah.
So we can reduce the bit from the picture, so
Mm.
we compress the picture, right?
Yep.
Okay.
That's the reasoning.
Okay. Cool.
Okay.
I think I'm sure what should I ask? Oh, also for the
My friend's dead.
oh yes, we always like that. For the subpixel estimation, I don't quite understand what is that here.
Okay.
Yeah, I go through. I understand that motion. I go through that, but when I go here,
So-
I stuck
Okay. So the objective is to find
the pattern.
the best match
Yeah,
from,
correct,
from
correct,
an array of
correct.
pixels. Okay.
Yeah.
And it doesn't matter where that pattern, where that set of pixels comes from, right? As long as if we get the best match, then we use it.
Correct.
Yeah.
Yeah.
You happy with it?
Yeah.
As long as the encoder and the decoder can generate the same prediction.
But from your previous slide, if we want to find a match of a pattern, for example, the fish here,
Yep.
I think for the designer, we have to design a square, like how big is it, and then to find the best match.
Yep.
Right. So
Yeah, that's right. But
if we refer to the subpixel
Mhm.
here, so how can we, if we're using the fish here as an example,
Yep.
how does it bring
well,
the estimation?
let me just go through this explanation again to see if it helps. So if we think about trying to do this in one dimension, it's just easier to visualize what's going on.
Yeah.
So this is our object that's been sampled at one particular time,
correct.
and this is at a different time. And because
To the top. Yep.
it's a different time, it's not aligned. This rising edge is not aligned with the pixel sample location. So in this case, we just happen to have a sample part way up the slope, right? Here we don't, right?
So you mean here is more longer than this one?
Well, I mean, it's not, the position of this
Yeah,
is not relative to that analog curve
yeah,
is different to the position of this one,
Yeah,
just
correct.
by pure chance.
yeah, yeah, yeah.
So if we think about trying to do motion estimation between these two one-dimensional objects, our
Yeah.
objective is to try to shift one relative to the other until we get the best match, right? But that might be a bit difficult, not because they're describing different shapes, but because they happen to be sampled at a different time,
Correct.
right?
Yeah.
Okay, so what if instead of using this set of samples, we try to shift and interpolate and guess what the half pixel sample points would be. Right, so we generate these red samples
Yeah,
based on the blue. Now we can't generate new information.
Yeah.
We're not resampling. We're just saying let's interpolate in between the blue ones and get this red set.
but is the first red one is still between blue? Or is it not? Yeah.
No,
Seems
we've
not.
only got the blue samples,
Yeah.
but we're interpolating between to estimate.
Oh, yeah.
Right? And in this is an artificial
Oh, okay.
example, of
Yeah,
course,
okay, okay.
but intended to illustrate the point. But in this case, we could probably get a better match between this one and this set because we have a sample point that is better aligned with this one that's halfway up the
Yeah.
rise. Okay, so so to carry that across the two-dimensional case with images,
Yeah.
once we've got the best match we can find with integer pixel movement, and it happens to be on this set of pixels, we could then just try interpolating the sample points in between these integer ones, even though they don't exist, right? We're just interpolating to estimate them.
Yeah, but if we don't exist, how the computer or the machine can
Well, it can just take the
define
take
the-
the average between these two, and take the average between these two, and then take the average between these four to get that one, for instance.
But for the pixel, the computer can represent by a number like
Yep, yep.
X, Y,
Mhm.
and so say, oh, this put the, but how these two details. Yeah, anyway, the computer know the position. They has a way to define the.
Yeah, it knows the position, but it doesn't
Yeah.
know the pixel value. It needs to estimate the pixel
Yeah,
value.
yeah, correct,
right?
correct.
Okay, so if it estimates by taking these averages, it interpolates to find the half pixel
Yeah.
set of values, and then it tries to do a match again. So supposing that we, to get to here, our motion vector would have been, say, 3 pixels down and 4 pixels across.
Yeah.
Right? Now it's just doing another test to see how good the match is if we made it 3.5 pixels across and 4.5 pixels down, something like that. And because this interpolated set of points was obtained by the encoder using exactly the same pixel data that was sent to the decoder can do the same thing. So there's a chance, it might not, but it could generate a set of pixels that gives a better match than the integer pixel one.
Okay.
And so if it gets a better match, then we end up with a lower average prediction error, and we could save some bits.
Yeah. Okay. But in here, I can see if we're using the red line here to do the prediction.
Yeah.
So we go 1, 2, 3, 4, 1, 2, 3, 4.
Yeah.
So we got 16 pixel here.
Yep.
So our computer using this 16 pixel to do the match.
Yep.
Right. So if we're using a half pixel, we only using 9 pixel.
No.
Is that-
No. So we're using 16 pixels, but we have estimated them. So they are 1, 2, 3, 4,
Okay.
5, 6, 7, 8 over here. Sorry, 5,
6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Right?
Still 16.
Yeah. But it could also try shifting the whole thing half a pixel to the left and then try that set of pixels as well. I understand what's confused you because of this drawing. But the intention was that we interpolate a set of all these half pixel locations everywhere around our integer pixel best match, and then we can try all these combinations or try shifting the around to see if we can get a better match at half pixel resolution.
But so because you draw the picture like that, so
Yeah.
physically
Yeah,
between each pixel,
Yeah.
it's nothing there.
that's right. So,
Correct.
So,
So-
yeah.
yeah.
So we're just averaging to estimate what was there. It's like this. Right? There was nothing there
In
either,
between, yeah.
but we just estimated it. We averaged it, and in this case,
okay.
it happened to give a better match.
Probably need to think about that.
Okay, all right.
Yeah.
But I'm just trying to understand, show how to. So if we were thinking about testing to see if this blue set of 4x4 pixels could be best matched at this point, we would be using these 16 pixels. Right?
But
And,
physically, there's no pixel.
No, I know,
Yeah.
but they have been interpolated.
Yeah,
So,
interpret. Okay.
and it doesn't necessarily have to give a better match, but it may give a better match. And if it does give a better match, then for the sake of telling the decoder, you also should interpolate pixels, and we'll end up with a better match, then it's worth it.
Okay.
So think about it a bit.
For this one, because not much information from internet.
No?
Not too much information. They're talking about something else, but relate to it, but it's not typically talking about this.
Oh, okay.
Yeah.
There might be something in one of the textbooks I suggested that you
Okay.
can find in the library. I better
Alright.
restart.
All right.
I'll catch you at the end if you want.
Yeah.
Okay, rather a longer break. Sorry. Let's continue. So what I'd now like to talk about is now that we have a feel for some of these basic coders and the tools that are used and what's generated, let's consider what rate is generated by a video coder. And so starting with this question, if we remove redundancy, and that's our objective, if we remove redundancy from our sequence of video pictures, will all of them generate the same number of bits? Like, will we have 4,000 bytes for every frame? We won't, will we?
No.
Right? Why not?
Because you said you are moving redundancy. You are moving the picture.
Yeah, the amount of redundancy will be different for different pictures. Right? So,
Depending on the picture information.
All pictures.
yeah, all pictures in the sequence. So some pictures will have more high frequency components than others. Some will have, and then a video sequence, there will be more motion in some parts of the picture than others. And then some parts might have a scene change where the picture changes completely and we can't even predict it from the past. So so the information content varies in any real video sequence, and so does the generated bit rate. So the number of bits per frame is going to vary. And in fact, if we if we fix the quantizer, if we use the same quantizer for a series of video frames, then we get this sort of rate variation on the output. This happens to be using the MPEG-4. We will talk about MPEG-4 later on. Doesn't matter what the source is. Obviously, it's Jurassic Park. You can just look at that plot and see that's Jurassic Park. But the important thing that we want to learn from this is the degree of variations. This is the number of bytes to describe each frame. And we see some quite different characteristics along here. What do you think these spikes might be?
Eye pictures.
Eye pictures, well done, that's right. So every half second or so, remember, we put in a keyframe, an eye picture. And so these, and because they're encoded independently of all the others, they require more bits. And so we have these spikes periodically every half second or so. Why don't you think we see those spikes here? Why do you think we wouldn't see those same spikes here? Well, I don't actually know the exact sequence of the movie, but I think we can guess what's going on.
The screen is all black or something.
Well, it's requiring quite a lot of bits, right? More bits than anywhere else in the sequence.
Pictures are the same.
I,
Both the same.
well, I suspect that there's
Pictures are same, then there should be the low bits required.
which one?
If the pictures are same,
Yeah,
we need to low bits.
that's right. So this probably not a lot is happening here because for predicted pictures, the rate is quite low. So these are our P's and B's in here somewhere. Every time we get an eye picture, we get a spike, but in between there's very little information. So that's probably quite a still scene. But what do you think's happening here? I mean, it looks like because the eye pictures and the B and P pictures are not standing out, it's probably very hard to predict each picture from the previous one. There's probably a lot of action. There's probably a dinosaur ripping people's limbs off or something, right? Or lots of scene changes every half second or faster, and people running, and it's just very hard to perform prediction from one frame to the next, and so we don't see this such a clear distinction between I's and P pictures. Okay, so that's looking at the what's going on in the coding, but it's also interesting to see this significant variation of bitrate throughout the sequence. So what rate do we actually, what do we do about outputting our the rate that is, or the bits that are generated if we're generating a variable number like this? In practice, we wouldn't allow a coder to run completely open loop. By open loop, I mean just fix the quantizer and just accept whatever bitrate it generates, because we can't put limits on it. We can't control it. And if we have a sudden spike in the bitrate here, that might be generating bits at a faster rate than we can actually store on disk, possibly, or burn onto an optical disk, or our interface rate into our network might not be fast enough. So we would put some sort of buffering, and we would have a feedback mechanism to make sure that the rate didn't exceed certain limits. So the idea is that our encoder, as we've described before, encoder, as we've described before, is sitting here. We've got an input video signal. If it's generating a variable rate, but we have some parameters that we can control. Most obviously is the quantizer. If we allow that to go open loop, then we would have an uncontrolled output variable rate. So ordinarily the configuration would be something like this, right? So just ignore that constant rate for a moment. Whatever our network interface or storage device interface or whatever it will be, we feed it via a buffer, and we're constantly reading stuff out of here, and then but filling it at a variable rate defined by the image characteristics, the video characteristics, but also by this control parameter. And as the buffer contents varies here, if it's not getting close to overfilling or not getting close to emptying, then we might allow the quantizer to stay more or less fixed. But to make sure that we don't have that situation where the buffer overflows or underflows, we might control that the behaviour of the encoder using this quantizer. Why not just use a really big buffer? Well, we could, in that circumstance, we could essentially let the encoder run almost open loop, but it's a balance between the delay, right? If we have a big buffer, we've got a big delay, and it could be costly, and there are quality trade-offs. So ordinarily we would run with a modest-sized buffer. And just to reinforce our understanding of what would be going on there, I'm trying to plot here how we use our throttle, our Q parameter, according to the buffer fullness. So for a lot of the time, if the buffer fullness varies over some limited extent, doesn't become too full and doesn't become too empty, then we would leave the quantizer more or less the same, because that would give us, roughly speaking, the same quality. But if the buffer was almost empty, because because there was a period in the video where only a very small, very low rate was generated for a while, then we would need to generate bits, not because the video demands it. In fact, the video is being encoded at a fairly low rate at that point, but because we need to make sure that our buffer doesn't empty completely. Otherwise, we're trying to read bits out of an empty buffer to transmit them. So we need to reduce the size of the quantizer, step size, to generate more bits, just to make sure our buffer doesn't empty. And the reverse would also be true. If the buffer became very nearly full, we would need to set our quantizer to be a large step size. As a result, we would reduce the bits. We'd also reduce the quality, of course, right? But that's necessary to make sure that the buffer doesn't overflow. And then we just join the components together. So that would be the rough form of our function. It would determine the value we give to Q based on the fullness of the buffer. But I said that I asked you to ignore the bit about constant rate at the right-hand side of that earlier diagram. But it is there are both situations possible. So let me go back for a second. So there are situations where we have to deliver a constant rate. What would be an example where we have to deliver a constant rate? All right, what would be a situation where we can deliver a variable rate, or could deliver a variable rate?
Variable rate is like action.
Yes, but I'm thinking, sorry, I wasn't clear. If this is feeding a network, say, a network connection, or a radio link or something, under what circumstances would that be a fixed bit rate, or under what circumstances could that be a variable bit rate? So if I was streaming video over the internet, for instance, what do you think would be the case?
Changing rate.
Yeah, we can within limits we can accommodate a variable rate, right? We can just send more packets per second if we want during the busy period because the network is packet based and provided we're not limited by our interface rate into the network, for instance, we could send a higher rate when the video is more demanding, and if there isn't much action, we might as well save bits and only send a smaller number of packets. What's a situation where the rate would be constant though? That would be fixed. Maybe it's not quite so obvious, but
Downloading some videos.
well, if you're downloading a file, you don't really care if the rate varies in between, so there's no
Network is congested.
Pardon?
When network is congested.
Oh well, yeah, that's a different situation. If the network is congested, if this was feeding, if we had this connected to our internet interface,
So
um,
decoder has enough time to decode.
sorry,
Enough time to
needs enough time to decode.
good enough time. If your rate's too high,
Oh, okay.
it's not
Yeah, sort of a flow control type problem. Possibly, but we could say that. Okay, this is a bit of a side issue, but we can. No, that's all right. It's important. We could say that if the video, if frame X requires a certain number of bits to describe it, even a very high number of bits to describe it, then the decoder would have to read that number of bits in that time interval to be able to decode it and display it anyway. So, assuming encoder and decoder are matched in that sense, that shouldn't be a problem. No, I was thinking more in terms of something like a TV broadcaster, right, who has this fixed bit of spectrum, this fixed channel that's available to him or her. And we'll talk about TV broadcasting, digital TV broadcasting, right, nearer to the end of the semester. But essentially, they have a fixed bit rate available to them. They've got, say, in Australia, it's a 7 megahertz chunk of spectrum, and that turns into about 20 megabits per second, and they can do whatever they want with that, but it's fixed at 20 megabits per second. They would want to be, in that case, they would want to be reading this data out at a fixed rate. It's a little bit more complicated than that because they actually combine several TV channels together, or programs together in the one bit rate. But it's a good enough model for our heads. Okay. So let's think about the consequences of constant and variable bit rate in terms of the overall effect on the video. So let's assume two cases. So one is where, it's the variable bitrate case where we have kind of fixed our quantizer, and then where there's the low motion part of the video, the bitrate is able to drop, as shown there. But when there's high motion or greater complexity, then the bitrate goes up to accommodate it. And then the alternative case is that we've got this buffer, which is ensuring that the generated bitrate is constant. That's the CBR dotted line. So let's just assume that the area under the graph is the same, right? So the area under the graph gives us our total number of bits, right? It's bits per second times seconds. So if those two areas were the same under the dotted line and under the solid line, which do you think would give the overall the better perceived quality? Or do you think you can draw a conclusion about that or not? Better perceived quality. There's emphasis on the perceived. What was that? CBR? Why?
See, maybe the value of DDR, because like if like the eye, I mean sometimes
So, yeah, well, what the VBR is doing is where we don't need a high bit rate to give an adequate representation of the video, we can drop the rate and save bits. But when we need it, then we provide it. If you think about what's happening in the CBR case, though, in this segment, just to ensure the constant rate, the CBR one is actually sending a higher rate than is needed. Okay, so yes, we're getting a higher quality reproduced on our screen, but we can't necessarily take advantage of it anyway. Right? It's sending a higher bit rate than we need. On the other hand, during this higher motion segment, the VBR is trying to maintain constant quality, more or less, and the bit rate is increasing to allow that, but in the case of the CBR, we're throttling back on the quality. We have to make sure that our buffer doesn't overflow, and so our Q control is making the quantization more coarse and dropping the quality a little lower. So the result is that we will, to a first approximation, I think you understand this description's a little bit general, but to a first approximation, this number of bits per second will give us an adequate quality, but we're sending more for CBR, even though we don't need them. In contrast here, we need this number of bits per second to maintain quality, but we're sending only the lower rate for CBR. So overall, we would expect that the CBR quality for the same number of bits would be a bit lower. So when would you choose constant bit rate and when would you choose variable bit rate? So it really depends on what's important. It may be self-evident, but is the instantaneous rate what's really important, or is the total number of bits what's important? If we have a budget in terms of the total number of bits available, then we would want to encode as with variable rate for the reason. What's an example where our budget is the total number of bits? The clue is it's not a network.
Maybe it's DVD.
A DVD is exactly right. So with a DVD, we have 4.7 gigabytes that we can store on this disk. There's a limit to how fast you can read it, but what's really important is how much you can get on this disk. And so if you can save on that total by allowing the rate to increase and decrease according to the content of the video, then you would do it, and indeed you do. So the bit rate that's that DVDs are stored at is varying with a maximum that's around 10 megabits per second, limited by the interface rate. But if the video has low complexity, low detail, then the bit rate drops accordingly. The second dot point, do I only have a fixed rate channel available? So that's the broadcast TV case, or maybe I've paid for a fixed rate channel, so I'm going to use all the bits that are available to me anyway, in which case I might make it variable rate. Is there an opportunity for statistical multiplexing of variable rate streams? So you come across this term statistical multiplexing before? No? So if we have multiple sources that are varying in rate, but we're able to combine them together on some bearer, on some network, then because they don't all have the peaks at the same time, they tend to smooth out somewhat. I've got a graphic to show that, I'm pretty sure. Yes, there is. Next one. So, in general, we would use CBR for transmission over a network. That's a bit too general, really, because a packet switch network like the internet can accommodate a variable bit rate. But if I've leased a line from a telecommunications provider that gives me X megabits per second, then I would use constant bitrate. But I would use VBR for stored media, for DVDs and Blu-rays, and sometimes satellite, and the sometimes satellite comes from this statistical multiplexing that we'll talk about with the next slide. So this illustrates the statistical multiplexing thing. So this is the result of obtaining many of those trace files, as I showed before for Jurassic Park. If we look at a number of traces for the variation in bitrate from along a certain number of frames for a number of different movies, you can see that if I take the extreme example, maybe this blue trace, what is it, Star Trek First Contact, or the dark green one, which is Star Wars 4, there are very large variations in bitrate if you think of it in terms of a percentage. So maybe from on the dark blue one, it's Jurassic Park again. Anyway, so it's these. It's a bit of a worry when you start to recognise the movie from the trace plot. But anyway, you can see that the peak is perhaps 5-6 times the lowest rate here, and maybe it's even greater for the dark green one. But suppose we were encoding lots of movies, or several movies, and then combining the bit rates together on a higher rate channel, and then broadcasting them all at once, which is what you can do in a satellite transponder. You've got around 54 megabits per second available, and you can send many TV channels in that space. So when we add up all the bit rates together, we get this, the plot at the top, which, although it's varying with this crude illustration, the variation is much lower, right? Our peaks are about maybe 20%, 30% higher than the troughs, but they don't vary by a factor of 5 or 6, as is shown there. So we're getting this smoothing effect, and this is statistical multiplexing. The multiplexing is based on the statistical variation and the assumption that a high peak in all of these sources is unlikely to occur at the same time. But it is possible, right? We need to accommodate that possibility, and so a bank of encoders that feed a satellite transponder might look something like this, in principle anyway, where they share the same buffer. So, so all of these encoders are operating at variable rate, and provided and we're reading out at this constant rate, 54 megabits, say, for the transponder. Provided the buffer doesn't exceed certain parameters, we just allow these things to continue generating a variable rate. But if this buffer starts to overflow, or starts to get near full, then our rate control kicks in, and we might adjust these quantizers to just make sure that we don't overflow. And we can adjust them differently for these different sources. So, you know, the one that makes most money, maybe you maintain the highest quality, or if it's sports or something like that requires high resolution, you may leave that one unchanged, but you could reduce the quality on the movie, because the movie's generally a little easier to encode, that sort of thing.
So the constant rate is the output of the multiplexer. The multiplexer is...
Yeah, that's right. So we're effectively multiplexing in this buffer here, right? And that's feeding the satellite transponder. Yeah. Okay. And so, yes, that's just some nice animation. And there's another illustration of the statistical multiplexing principle without using real data. But if we wanted to maintain the available bit rate for each of our 4 sources there to accommodate the highest quality we required, then we would require this much bandwidth. So that's the CBR option, the constant bitrate option. But because these peaks don't always occur at the same time, we can accommodate a varying rate, and the total is somewhat lower. said the same thing before, but it just...
The total is fixed.
The total is fixed in that case, yeah. Okay. So I've waved my hands around a lot about video quality. How do we actually measure it? If we could characterise the human visual response, then we could build that whole thing into our algorithms, and everything would be mathematically deterministic. Right? Ideally, this is what we'd like to do. We'd have our input pictures, they go into this encoding engine. We assume an output buffer there, and we control that encoding engine according to our model of the brain, right? So we've got this target bit rate that we want to achieve, or maybe we allow it to go variable, but we've got a vision model that takes account of the psychovisual system of the brain, and if we could determine what would be visible in terms of distortion, then that is what we would use to control what parts of the picture are distorted when we want to save bits. Yeah? It's just, in principle, that makes sense. But the problem is that mathematical characteristic of the characterization of this human visual system is a really hard problem. It hasn't really been solved. There are lots of efforts that have been carried out. There are standards groups that have tried to come up with better measures than just signal-to-noise ratio. Signal-to-noise ratio is a useful indicator of perceived distortion, but it isn't very accurate, particularly for low-rate, low-quality video. The signal-to-noise ratio is pretty poor. So there are other measures that people have developed, but it's a long way from being a solved problem, because our psychovisual system is very complicated, and we are sensitive to particular types of components in images. So we're highly sensitive to edges, for instance, and lines in particular directions. And two different people might be looking at the same decoded video, and one of them's looking at one part of the action and one of them's looking at the other part of the action, so you don't even know where the focus is applied. So it's an unsolved problem, and for that reason, when people go to standards bodies such as MPEG, the group gets together and one guy stands up and says you should use my coding technique because it saves bits and you can't tell the difference in quality. How do we assess it? Well, in fact, they use what you might think is quite a crude method or mechanism, which is formal subjective testing. So it's quite complicated and costly, but it does turn out to be reliable. So the idea is you get lots of people that you sit in front of monitors, TV monitors, with having too much fun at it. With highly controlled viewing conditions, so they are setting a fixed distance from the screen, and the surrounds around the screen are illuminated at a particular level of grey, and all this sort of stuff is all controlled, all defined by a standard there. And they either have electronic meters or a piece of paper that they fill in what the quality that they perceive in between two randomised examples of a little video clip. So that turns out to be surprisingly reliable. It can be reproduced even in different countries with different video sequences and stuff, but it is quite costly to implement. You have to screen people to make sure they're not colourblind and this sort of thing, but you also average. So you have lots of subjects and you average, and you always remove the outliers from the data. It's all very well managed statistically. But interesting, just to I think an interesting little side story about this is that when I was actually involved in the development of MPEG-2 in a small way, so I went to the meetings, and so when they were deciding on the tools to include in MPEG, they did exactly this. They had all these standard test sequences that were about 10 seconds long or 20 seconds long, and they chose a variety of different materials, so some that is relatively easy to code, some with high complexity, some with panning cameras, and some with different motion in different directions, with rotation and translation to test the motion compensation and so on. And they did all these tests. They decided what tools to include, and they finished the standard, and it went into became an international standard, and people started making chips, and then they started using it in TV studios, and only then did they find that there's a fade. Right? When you fade from one scene to another, you reduce the intensity to black and then bring it up from black. And from what you understand about predictive
Coding and motion compensation, you would realise that though as you fade to black, the next frame you're about to encode is very similar to the one before, but it will give a poor match to a motion compensation check, to motion estimation. And so it was just an omission. It's just hard to predict these things in advance. Anyway, how are we going? 7:16. Well, the bad news is that we've got a little bit more time to get on with some other material. So let me just stop that slide pack, and I'll go on to the next one. I apologise that I haven't got this one up on the LMS yet, but I will have it there shortly. And we'll make a start on this one. So, oh, sorry. Did I not show any of those? Oh, what's happening? Ah, okay. There we go. Yeah, sorry. So I will change the title slide, but I wanted to just start off by introducing it, not the same level of detail, but talking about some of the more significant video coders that are around today. I'll try to put them in context as we go through them and talk about some of the proprietary ones, and this open source one that I mentioned last week, this AV1 coder that has emerged from a collaboration between those big players: Adobe, Microsoft, Apple, Google. So let's just start off with the current range of standardized ones. So going on to the next set of standards. So we've worked down to MPEG-2, H.263. You might guess from the terminology, the fact that it's given this code H.263, similar to that one, but this came out of the ITU as well, and indeed it did. And I won't bother talking about the others now. We'll meet them later. So, so H.263 is still used today in various applications. It's a more efficient version of, and therefore a replacement of H.261, again intended for communicative video, so video conferencing, video telephony. But it's also found use in other internet video applications. It was intended to be fairly robust, so with the telecommunications focus, it was intended to be suitable for network operations, so IP networks in particular, and mobile applications where the bitrate is reasonably high, and operate over quite a wide range of bit rates. What are some of the features of H.263, particularly comparing it with its earlier cousin? It uses half-pixel motion compensation, so that wasn't result of the experience and more processing power available. Improved VLCs, that's kind of detail. I think when we talk about this, sorry. Okay, so when motion vectors are coded, I don't think I talked about this before, but you would expect a fair bit of correlation between the motion vectors in adjacent blocks. So if a large part of a picture is an object that's all moving in one direction, more or less, then the motion vectors will be correlated, as will the pixels. And so for that reason, the motion vectors would typically be encoded in a predictive sense. What's the difference between this motion vector and the previous one? The third dot point here is just saying that there is a more sophisticated way of doing that prediction, not just from a previous neighbour, but from other neighbours. More picture formats as we get closer to modern times, where it's easier to accommodate a wide range of picture formats instead of just the standard TV ones, and a number of options. And this is really where I want to concentrate, because it's not really essential that you memorise what's inside H.263. I just wanted to highlight the new tools that were introduced here and understand why. What are the advantages that they have? So I'm really using H.263 as a kind of a tool to place these things in context. So one of these tools that was introduced there is called unrestricted motion vectors. One of the limitations of motion compensation that you might recognise is that one's tempted to say, of course, but they don't allow you to point outside the picture area. And you might say, well, of course not, because there are no pixels there to use for prediction. But we could have a situation such as this one, where if we think of working on macro blocks from left to right down this picture, when we're encoding, sorry, let me just get this going. If we're about to encode, say, this macro block, then it would actually be useful to be able to grab those pixels from the previous frame, right? Just by chance, the pixel values would work as a predictor. But traditional motion compensation would say, well, no, you can't, because you're trying to pull pixels out from outside the frame boundary. But this concept of unrestricted motion vectors allowed you to just interpolate, or actually fill in, using the edge pixels to fill in that array. And if it's useful, then you can use that as a prediction, right? So you can define a motion vector like this. I'm not sure if this is a tremendously important point, but we might as well talk about it. Do you think this would be most useful for high resolution pictures, like high definition, or low resolution pictures?
High resolution.
Why?
Because low resolution, it doesn't matter where it is from. It's in low bit rates.
Well, yeah, okay. So there's a question of quality. I think you're talking higher quality and lower quality, maybe? Yeah. Any other thoughts? Another way to look at this would be what proportion of your macro blocks are going to be on the edge. And in fact, as you reduce the resolution, the size of the picture, then a larger proportion of the total number of macro blocks would be actually on the boundary. And so it'll probably make a bigger difference for lower resolution pictures. For an HD picture, yes, you've got you are restricted for all of those edge macro blocks if you can't do this unrestricted motion vector thing. But there's a smaller proportion of macro blocks that are affected anyway, so maybe it's not so important. Okay, anyway, interesting additional tool. And another interesting additional tool is this one, whose name is overlapped block motion compensation. And don't be frightened by the name, we'll investigate where this comes from. If we have a set of pixels that we're trying to predict using motion estimation, then the block of pixels that we match is a block that's centered in a particular location, and so the vector is going to be based on the pixels surrounding this this center pixel up to n over 2 over root 2 pixels away, if you like. So the closest pixels, the pixels that are used to generate this motion vector will come from, will of course be neighbors to this center one, that's but the most distant ones will be that diagonal, which is n over 2 root 2 pixels away. Why is that important? Well, we're using that same motion vector. It's calculated based on matching all of these pixels surrounding this this center pixel, and we're using that motion vector to predict these pixels right at the edge here, and that they might have more in common with other pixels out here than the ones that are dominating in the motion estimation calculation. So if the motion vector is not very accurate for those particular pixels, it could lead to these problems where we have less accurate prediction, we start to see the blocking effects, and we have greater errors near the edge of the macro block than in the center. So if you don't completely understand where this is going, just wait for a minute. I think the next graphic will make it more clear. So the idea of this overlapped block motion compensation is that although we send only one motion vector for every macro block, we actually calculate one for every individual pixel based on its location in the block. So how does that work? So the idea is that we assign a motion vector to a pixel by a formula that depends on its particular location. So here are three macro blocks with associated motion vectors in vaguely the same direction but slightly different ones. And we're going to decide for every single pixel in this new block that we're encoding what motion vector we use to predict it. So I really need to emphasize that we're not sending a separate motion vector for every pixel, but we are using these three, the neighbouring ones, or those from neighbouring macro blocks and the one that's associated with our current block, to calculate a motion vector to take a pixel from somewhere else, just one pixel from somewhere else in the frame used for prediction, and translate it to here to use it for the prediction. Okay, so we would take those three motion vectors and we would create a weighted sum, and the weight would follow a formula that both encoder and decoder know, determined by this pixel location, and it would come up with this weighted sum, a single motion vector, and that would be used to predict this pixel. So again, the logic is that if we only use that single motion vector to represent all of these pixels, it ignores the fact that these pixels up here probably have more to do with this block and this block than the pixels that we were mainly used to determine this motion vector. So what's the result? If we look at the mean square error as a result of the motion estimation for averaged over lots of blocks without this overlap block motion compensation, then we see that the error tends to be larger towards the outside of the blocks there. You see that those peaks in the three-dimensional graph. When we do this overlap block motion compensation trick, then it tends to flatten out. So the error tends to be approximately equal, independent of the location of the pixel. Does the process make sense?
So for every single pixel, we need to send motion vector.
No. This is the
Calculate the motion vector.
we need to calculate a motion vector, but not send it. No, because we send one motion vector for each macro block, and then both encoder and decoder know the algorithm based on that location. It happens to be in location 2, right, in this macro block, to find the weighted sum that we will use for that. Right. Okay, so it doesn't involve any additional transmission over here. We've got the same number of motion vectors. It just involves a calculation of the appropriate motion vector to use pixel by pixel. So there's more processing, but it has this gives this advantage that the representation of the edge, the outer pixels, is a little bit better.
What about the center pixel? Like they need to do that for even the center one.
Well, I can't. I have looked at these weightings, but I can't remember what they are. Of course, I would imagine that the weighting for this one would be very close to just using this one. So it can't be any worse than this result, but it may be better depending on the location of the pixels. That looked like a question. Is it?
What he was asking is, pixel is at the center of that, the three boxes, three edges.
Oh, yeah.
Then what is the region?
You mean sort of up here?
Yes.
Well, again, it would there would be a formula that puts appropriate weighting on. There will be increased weight from this one and this one compared with this one because it's a close neighbour of these. Right? So you understand the principle, because we're defining when we calculate. Let me get rid of this. When we calculated this motion vector for this block, we did matching based on this entire range of pixels, which is the sensible thing to do, but it means that we don't take account of the fact that the pixels up here are probably more closely correlated with the motion that these ones are having.
So it will generate a new motion vector. It's not going to use one of those. It will generate a new.
It'll generate a new one that's based on a weighted sum of these ones. Yeah, and they're calculated pixel by pixel. Yeah. Okay. Another tool that's used in H.263. Keep that little label up in the top left so we can just remember what we're talking about. And I must remember to finish it in a reasonable time. One of the limitations of, or one of the reasons we have spikes in bitrate and large bitrate generated in video is because of these keyframes. These eye pictures always require a lot of bits. So it would be good to find ways to reduce the number of bits that are used to encode those iframes. And in fact, we've already talked about HEIC and HEIV. When I was talking about still images, or am I confusing myself? Possibly confusing myself, don't worry. There's a new range of a couple of different new still image coding methods that are replacing or starting to possibly replace JPEG, and they have come out of efforts to improve the intra-coding in video. So the most recent video coders have generated or have spun off an efficient way of encoding still images, and Apple in fact is using that now for internal storage of images in the latest iPhones and latest Mac OS. Anyway, so that's why it's a good thing to be able to reduce the bitrate for those intra-coded pictures, those keyframes. But we have a challenge, of course, because we can't take advantage of correlation from one frame to the other. These intra-coded frames have to be coded independently of one another. But we can look for other correlations within the frame. So that was what was done with this technique called advanced intra-coding. So the DC coefficient of our transformed block, these DCT coefficients, is likely to be similar to neighbouring blocks because it's the average intensity of the block, essentially. And for that reason, it's encoded differentially. So for the DC component of each 8x8 DCT block, the coefficient is encoded as a difference from its previous neighbour. We talked about this in JPEG at least. But with the advanced intra-coding effort within H.263, they started to think, well, okay, what about some of these other coefficients? It's hard to predict AC coefficients in general between blocks because AC coefficients represent higher frequencies, and if there's higher frequencies, there's lots of change, and if there's lots of change, then one block is not going to be well correlated with the other. However, we can remind ourselves that along this row here, this represents increasing horizontal frequency in this direction, but zero frequency vertically. And so if there was zero frequency in one macro block, zero vertical frequency in one macro block, then it's probably going to be close to, well, no, it's not, then it's also likely to be zero horizontal frequency in, zero vertical frequency in an adjacent block because it's not changing very much. And so the idea was that we could predict these frequency components which have zero frequency in one particular direction, in the vertical direction or in the horizontal direction. And so that's this additional technique. We've encoded and transmitted the upper block and this block, and we can predict these this row and this column of coefficients based on their neighbours and look for any improved coding performance as a result. Make sense? Okay. Another tool introduced by H.263 is what's called a deblocking filter, and it has a similar kind of function to that loop filter in H.261. And the idea was that we can optionally include a filter here, particularly when we're operating at low bit rates and those block boundaries start to appear. We can kind of smooth them out before we use them to predict the next picture, and it's exactly the same reasoning as that loop filter in H.261. So the idea is to remove blocking artifacts. It's included in the prediction loop. So it's used for prediction. Does it need to be standardized? Bit of a mental leap in subject, but remember the justification for what we standardise, what we don't standardise. Do we need to standardise this?
Like field
I like the way you started. Well, it's if it's in the prediction loop, then encoder and decoder both need to do the same thing. So we need to standardise it. It's essentially it's just applied to 2 pixels either side of the boundary. So where we have macro blocks, we just these are supposed to be individual pixels. We just perform some filtering across those pixels to smooth average out and make sure the block boundary is not too visible. It's a bit of detail just to keep you thinking. It's not specified in the standard for B pictures. Why is it not specified in the standard for B pictures? A bit of a hard one, this one, but you have enough information to answer it. We've said that it's in the prediction loop, so we think it needs to be standardized. But
because B pictures you use the I and P
yeah, you're really close to the answer. No, well, you're right. We use I's and P's to predict P's, and we use I's and P's to predict B's, but we never use, so far, we never use B's to predict anything else. So it doesn't really matter if there's some coding artifacts included, because it's not going to propagate. But so as you see with the black writing, generally it would be a good idea to include this smoothing just to make the final picture look a little bit better. But it doesn't. It's not essential that it be included from the point of view of compatibility and generating consistent prediction from encoder to decoder. Okay. Okay. I tell you what. I'll talk about MPEG-4 and then we'll stop. So, first thing to note about MPEG-4 is what happened to MPEG-3. Pardon?
There is no impact.
There is no MPEG-3. This is a little secret I'm sharing with you from the inner sanctum. Yes, in fact, there was MPEG-3 for a short time. What's that? Oh, no, well, no. That's a very good point. A lot of people think MP3 means MP3. It doesn't. We'll talk about MP3 when we get onto audio. But the MPEG committee had started this initiative to create or develop MPEG-2 for standard definition television. And at the same time, HDTV was just on the horizon, so they thought, well, we better do another one for HD. And so that was MPEG-3. And these initiatives started off for not for very long, only a few months, as I recall, when it was decided that the same coding techniques were applicable to both. Right, so that's why we ended up with those profiles and levels defining HD and standard definition. And so MPEG-3 was not needed, and so the number was not used. So that's why it disappeared, and that's why the next standard became MPEG-4. There are more bizarre stories about numbering, which I'll share with you as we go. But we should focus on the technology. So MPEG-4, in fact, offers many features beyond just video coding efficiency. It allows for object-based representation. So I'll describe this in a little while, but the short version is that instead of treating an image as an array of pixels, we can define specific objects within it, right, and encode them separately. Define their shapes, boundaries, and encode them separately. It allowed for interactivity, so the idea was that with increased interactive applications over the internet. You can sort of click on objects and get the opportunity to buy something or whatever. It also allowed for coding of lots of different media, so graphics and text and synthetic objects, not just natural images. Vector-based graphics, as well as images and animations, all these sorts of things. MPEG-4 was really a very broad tool set for multimedia applications, and in fact the video part was relatively insignificant. The actual story behind the MPEG-4 video is that the MPEG committee thought, well, we've just about done television and DVDs. What's the next challenge? So they thought, well, we want a really, really low rate video. So let's come up with the best video coding standard or solution we can have for just tens of kilobits, so 10 kilobits per second. So that was the number one priority on the list of requirements. And then there were all these other things that were down below. But as the work continued and people met and they offered their solutions, it was just really hard to do. H.263 had emerged, and it was very hard to do any better. And so, in fact, on the requirements list, the efficient video at very low rates went further down the list, and all the other things stayed on the top. So there are two video coding solutions in MPEG-4. So tell me if this is a bit confusing because it's all about the internal structure. But there was an MPEG-4 Part 2, which it's a video coding system. It is specific to MPEG-4, but it's very similar to H.263 with a couple of minor variations. So they allowed for even finer sub-pixel motion estimation, quarter pixel. They allowed for global motion compensation. So if the camera panned, for instance, it's useful to have one parameter to describe how to move all macro blocks in the previous frame or in the reference frame to predict the current ones. But the performance was about the same as H.263. However, there was a later, much better video coding solution which came out of ITU, an H series number, and then the two bodies worked together and incorporated it as another part of MPEG-4 Part 10. Another part of MPEG-4. So the bottom line is that there is the efficient version of video coding actually comes from this one, which is part of MPEG-4, but MPEG-4 includes lots of other stuff as well. So MPEG-4, H.264, I said I was only going to talk about MPEG-4, but there was only one slide, so let me go a little bit longer. Actually, I won't, because there's a bit of material there about H.264, and I'll end up failing to meet my objective. But this H.264 was an attempt at significantly increasing the coding efficiency, and it was successful in doing that, but it came at a price of significant complexity. It's now with our increased processing speed and cheap memory, it's easy. Our phones do this stuff, but at the time that it came out, it was quite controversial because it was. Some people said, "No, you'll never have enough processing power on a mobile phone to be able to do this." Anyway, the basic approach that was used to get this increase in coding efficiency was to make it highly adaptive. So instead of having fixed block sizes, as we've described before, they allowed for hierarchically defined blocks. So instead of having a fixed 16 by 16 macro block, I will finish in a moment, but I'll just get the graphic. It allowed for 16 by 16, but in certain parts of the picture, maybe that's that doesn't adequately describe the motion. So let's allow it to be split into two 16 by 8s, or maybe we can split it into small ones. So if we do this, of course, it involves more searches, it involves more motion vectors, but it is also more flexible, and so the encoder can decide, is it worth all this splitting these things up and having all this extra overhead to improve the prediction? And generally, if you can improve the prediction, you save bits. So we'll talk more about the tools that were included in H.264 next time. So I'm sorry that was a little bit fragmented tonight, but I'll get this slide pack up and the rest of it in the next few days, and let's finish there. But remember, we have this this test next. Everything up to now could be included in the test.
Is it going to be the first part of the lecture, the test, or the second part?
The first part, if that's okay. Okay. I think it's probably best to get it out of here.
Is it 1 hour and a half?
No, it's half an hour. Oh, half an hour. Okay.
How many questions?
I don't know, actually.
Multiple choice.
Certainly not. No, it's not that difficult. I have to write more questions to make it more challenging.
Is it the multiple choice question?
That I'm going to let you know in the next few days. So let's say it's the first half hour of the next session, and then we've got another project progress test, sorry, in week 9. So we just split it up, so it's not too onerous. Okay, thank you guys. With which slide?
Interlace.
Oh yeah,
coding.
yeah.
This one. I kind of forget what the purpose of the interlace.
Oh, okay. What the purpose of the interlacing?
Yeah,
was?
interlacing with
the first one.
what's the purpose? Yeah.
Okay, so it was it came from analog days,
Yeah.
right? And just thinking the best way to describe this. The objective was to have as many scan lines as possible because we want high vertical resolution.
Yeah.
But we don't want. We wanted to minimise the number of frames per second because of the limited bandwidth available and the limited processing that was available. And so the solution was to split up the frame into these two separate fields and sample them at different times. So that way, if you think of a scene that is not changing very much, the best example is just to think of it for a fixed scene. Then by scanning the odd fields, the odd lines, and then the even lines, and then the odd lines, and the even lines, the picture has the same resolution as if you were scanning more than one frame.
Do we display the two pictures one by one or at the same time?
In the analog world, we would display them at different times as well, and that actually helped. But these days, with LCD displays, we have pixels that are on all the time. We're just updating what they are. So if we show one field and then another field, another field, another field, we see all these little jagged edges things. So that's the reason that we have some interlacing in the first place. These days, we're trying to get away from it. You know, the latest systems are all the HD, not all the HD, but 4K, for instance. 4K, very high resolution video. It's not interlaced as well. But given that we have all this material that is interlaced, and we still have TV cameras that are doing interlacing, we have to encode the output as best we can. And so, recognising that there are those artifacts that occur within a frame, if we put those two fields together, then come up with these different coding approaches. Does that help?
Yeah,
Is that
yes.
right?
Yeah.
Good.
I just have a small question. So is that vertical like resolution? Is it like pixel like this, vertical resolution, and that's horizontal?
Well, the way you're holding it, yeah.
That's vertical. Is that
Yeah,
vertical?
yeah, but
What about if I do this? Is that horizontal or
Well,
and then the
well, now that's the vertical and that's the horizontal. But,
then now it's like more pixel in there.
yeah, but there's the same number of pixels per centimetre.
Yeah.
The density won't be the same in both directions.
So that's horizontal. Is that vertical or?
These are horizontal pixels now.
Okay. That's vertical.
No. Well, I mean,
So I guess
what are we trying to do?
So what he was asking is,
Now let's say I
phone,
wanna
phone like
calculate
this,
Yeah.
so distance will change. I mean that.
Not in centimetres. It will be a different number of. You'll be calculating a different number of picture heights
Yeah.
as opposed to picture widths, but the number of centimetres will be the same.
I mean, if you're going to ask me the question in the test to calculate the distance of so I would say the vertical resolution, like the number of pixels over the, not as a height, but as a width height, I'm going to take the height like this.
Well,
If I want to do this,
yeah, but what I'm telling you is the answer in centimetres must be the same
must be the same.
because the sampling density is the same in both
Yeah.
directions, right?
Yeah, that's right.
Yeah.
Yeah.
So
No,
I
but
mean,
we got some difference in that answer.
Maybe
The d and d dash that we have calculated
yeah,
for the term phone is, I mean, something different.
there was,
24 centimeter, 26 or 25 centimeter.
well, yeah, I wrote something on the discussion board about that. I wasn't sure where those errors were coming from. It must be an error
Yeah.
because one person said that they had used the phone dimensions instead of the screen dimensions.
Yeah,
They're
it's
different.
Yeah.
Was it? Oh, sorry. But because the number of pixels per centimetre is the same in both directions, I don't think any phone does anything different. So they're square pixels. And if we assume all our calculations, we were assuming the visual acuity is the same as 1 minute of arc, then we must end up with the same number of centimetres as the further distance. So it just might be,
Okay.
it will be a different number of picture heights
Yeah.
or picture widths, but when you convert it back to centimetres, it must be the same. You know what I mean?
Okay.
So, where's mine? So if I did the calculation based on this as the picture height, then I might calculate, with using that number of centimetres, so 8 centimetres or something. I might calculate that the optimum viewing distance is, say, I don't know, 10 picture heights,
Okay.
right? But then I convert that to centimetres and I find that it's 27 centimetres. If I do the same calculation going this way, I might find that it's the optimum viewing distance is 4 picture widths,
Okay.
but the picture width is larger, so when I multiply it out again to get centimetres, I should get
Should be
27
the same.
centimetres or whatever it is.
No, but I meant when you do the number of pixels is you divide it on this on the height. If you wanna use this horizontal.
Yeah, what I'm saying is that it doesn't matter. It shouldn't matter.
Okay.
Right? You can do the calculations either way, just as
Okay.
long as you make sure you get the dimensions correct.
Correct.
What about the motion vector? Does it include when we send it to the decoder? So the motion vector has you said has a side information. Does it have tells the decoder where to search for the match, like
That's the entire. Oh, sorry.
like the motion vector? We say
Yeah.
normally we send the motion vector.
Yeah.
The encoder sends the motion vector to the decoder.
Yeah.
Is it to tell the decoder where to search for this block of pixels?
Remember, the decoder isn't searching. Right?
No, I don't. Yeah.
The decoder is simply told, take this block of pixels and use it for your prediction.
Like the motion vector, is it the coordinates?
Yeah.
Of the, has the
well,
coordinates of the.
It's the relative coordinates. It says, if I
Like you said, it has the side information vector.
no, it is side information.
Yeah,
It's
it is the side.
yeah. So if I'm encoding Sorry about the drawing, but this macro block, right, and I include a motion vector like that, then I'm telling the decoder that the block of pixels it should use from the previous frame corresponds to that block, right? So the motion vector consists of a pair of numbers. It might be -4, or depending on what's positive and negative, you know what I mean. Yeah. -4, -3. Okay, and we might actually represent it using Huffman coding and all that sort of thing, but that's not important. But the motion vector will have two parameters, which is the offset, so that when the decoder receives that, it says, oh, okay, I've still got this reference frame stored. I'll go to that reference frame. I'll find the macro block that we're just about to encode, but instead of taking these pixels, I need to take them from a position 4 pixels offset, 3 pixels offset. And I translate all of those. I use them for the prediction.
Yeah.
Yeah?
Yeah, I understand that when you said you send the motion vector, but then why the encoder send again the prediction error or something? If he sent the exact, the motion vector has the
because that will be a perfect prediction only if the motion is purely translation, and it might not be, right? If I clench my fist, that's not translation, and provided there's no lighting changes or no shade or nothing else changes. So it will give a better prediction, but it will not necessarily be a perfect prediction.
Okay, then.
So our prediction error signal is reduced, which is why we do it in the first place, right? Because if we didn't reduce our prediction error, then we would simply be sending more bits because we've got to send all these motion vectors now. But by sending the motion vectors, we reduce the average prediction error, and therefore the number of bits needed to represent it. And often we might be able to get away without sending any prediction error.
Thank you.
Yeah, that's all right.
Thank you. Have a good
No worries. You too. I'll see you next week. No, that's all right. I'm still early.